This is the Math 601 sort of lecture for January 21st. We're going to talk a little bit about two separate topics. This video talks about one topic, and the second or third video, depending on how this plays out, talks about some other topics. This is not meant to be a complete and total replacement for the lecture, but it certainly will get you some of the ideas. So this lecture is about least squares solutions in inner product spaces. So let's see here. What do we mean by least squares solution in an inner product space? Well, first of all, what do we even mean? Well, let's see here. So the goal is to solve ax equals b, where, and we've got a bunch of assumptions here, where b and x are in some inner product space, and a takes v to v is linear. You can think of it as a matrix, and that's very convenient for many applications. But it's not strictly necessary. Okay, so you'd like to solve this equation for x. So, solve this equation for x. Of course, there are many ways to do this. You can think of probably several of them, one of which goes under the name of Gaussian elimination. You may also have heard of Cramer's rule, which is not so computationally nice, but theoretically pretty solid. Or you could probably have played around with some other tricks. There's substitutions, especially if it's in a nice form. And if it's small, you can sort of bubble around until you get to the answer. Now, one of the things that you certainly have learned, and Cramer's rule is very nice to detect this sort of thing, sometimes there is no solution. So what do you do then? Well, if you're a mathematician, you say, well, there ain't no solution, I'm done. But if you're, say, an engineer or something, you might look at this and say, well, the reason why there's no solution is because there's maybe some mistakes in specifying A or B. So suppose we still want a solution. So you want an approximate solution. What if we want an approximate solution? Then what do? Well, we're in an inner product space, and essentially what we want to do is we'd like to know how close can we get. So let's see here. Let's recall some things here. So let's see, recall in an inner product. There's a norm. Oh, wait, what am I writing here? Inner product space. There's a norm. So let's see here. What is that? Well, the norm is written square root of like this. And what does that mean? Let's see here. Definition. A norm on a vector space W is a function. We usually write it with vertical bars. This here is telling you the input is in between the bars. and it's going to go from your space to the real numbers, and it's going to satisfy a bunch of axioms. What is it going to satisfy? Well, the first thing it's going to satisfy is this. It better be positive, and it better be 0 only if b equals 0. That's that non-degeneracy condition showing up again. The other thing that's true is that it's got some linearity type properties. See, if this guy here is a scalar in R or C, then this thing is actually outright equal to is the absolute value. And the final thing that makes it very normy is the triangle inequality. And both of these here, these are for all v, x, and y in my vector space. Okay, so those are the properties that make it a norm. For those of you who are in my topology class, what's the interaction between a norm and a metric? It's pretty easy to see. This is sort of a sidebar. A metric so normed spaces are metrics. Normed spaces with norms are automatically metric spaces. And you can check all the topology type axioms for the norms pretty easily. So it's easy to check axioms for a metric. If you want to play around with this and you get stuck, just come by and ask me. I'll work it through. But it's not too hard. Okay, end sidebar. Okay, so whenever you've got a norm floating around, you can talk about distance. Now, I just made the comment that inner product spaces are norm spaces. Oh, really? Well, let's see here. And in particular, so inner product spaces are normed spaces with a specific natural norm. With the natural norm given by the formula that I wrote up just before. That looks like this. So why is this a norm? Well, the thing you need to remember in order to make this work is there's something very special. So there's an important theorem. It's called the Cauchy inequality. And if you're Russian, there's another name beginning with a B, which I cannot pronounce, but it's something like B, something or other, ski at the end. And essentially what it says is it says that in this special norm, the inner products and the resulting natural norm play well together. Is that there's an inequality. The inner product between x and y, if you take the absolute value of that, remember it could be complex, but the norms are not, and so that's less than the product of the norms. So there's many proofs of this. I don't want to go into a proof right now. You can find one on Wikipedia, for instance. That's a nice one. The Keener book that I recommended has an extremely slick, like 2-line proof of this, which I rather like. If you get stuck, I'd be happy to show it to you, and maybe I will even show it to you in class, just because it's that cool. But I'm not going to spend time doing it right now, because I want to tell you about some other things. But But once you've got that, you can talk about why, in fact, this thing is a norm. So, why is it? Well, let's see here. Let's take a look at, well, we want to know something about x plus y, and we'd like it to show, this is a want, and the proof of this is, well, it's a standard kind of proof in this case. You square the norm, because there's square roots involved, and that's nasty. So we square it. So this is x plus y, inner product with x plus y. You make use of the bilinearity of this, or at least the sesquilinearity of it. So you get something like this, x with x plus y with x plus x with y and y with y. Okay, well, at this point, you take a look at this and you say, let's see here, what's what? In particular, let's see here, let's even, well, without too much terror here, this thing here is positive, so we can certainly throw absolute value bars around the whole works. And let's see, xx, oh wait, that is less than or equal to xx plus, and I'm just sucking the absolute values in fact. Sometimes forget I'm on a tablet. So we'll just add some absolute value bars everywhere. Okay, and let's write down the definitions of these. That's this one here. We'll hold off on a moment, and we'll hold off on this one. And let's see, there's y squared. Now we're going to use the Cauchy-Schwarz inequality. Well, what does that say? That says these two inner products in the middle here look like two like that. And then you say, hey, wait a moment, I could factor that. Oops. I could factor that. And then you just remove the squares and you are done. So the Cauchy-Schwarz inequality is really essential to see why this thing is a norm. Okay, enough said on norms for the moment. So let's go back now and talk about this optimization problem that we're trying to solve here. Remember, we're trying to solve ax equals to b, but we can't. Can't actually solve this. Okay, so what would be sort of another way to look at this? Well, this is supposed to be the same thing as ax minus b is equal to 0. But suppose really you didn't have that, it never was really equal to 0, so we really want it to be close to 0. So instead of being equal to 0, want this to be like approximately 0. Or put another way, our new goal is find the x so that ax minus b is as small as possible. But wait a minute, how do I measure the size of this thing? This is some abstract vector space thing, abstract inner product space elements here. Oh wait, I have a norm. Right. So I want to find so that norm is the smallest, and again, this is the natural norm. Okay, well, let's see here. Let's just pop it into the formula and try to see what happens. You know, we're trying to find ax plus b, ax minus b, ax minus b. We want that to be minimized. Well, how do you minimize things? Remember, this thing here is a function. is a function going from our inner product space V to R. It's a real valued thingy. Oh yes, I should know that I'm minimizing that. The square doesn't really matter too bad. Hence the name least squares, in fact. So recall this is a function like this. How do I minimize that? Oh wait, I use derivatives. Well, there's something a little funky going on here. We need a little algebraic ditty. Lemma is that if I'm taking the derivative with respect to z of x of z, y of z, well, this thing is a product. So it probably ought to follow the product rule in some fashion or another. So this is Leibniz rule for inner products. And what does it do? Well, it looks like this. You end up taking the derivative of the first one plus a, what do you know? And the proof is exactly the same, in fact, as you can find in your calculus book. It's just a straight generalize the usual proof. So if you want to know about it and you can't seem to figure it out, just ask. Okay, so why did I talk about derivatives? Oh yeah, I talked about derivatives because I'm trying to minimize. And when I do minimizing, you usually take the derivative and set it equal to 0. So that's exactly what we're going to do. We're going to take the derivative of this thing and set it equal to 0. Alright, let's go do it. So we're going to write, and let's see here, we're going to want to minimize ax minus b, ax minus b. Well, let's simplify this algebraically a little bit. It'll pay dividends. So let's see, ax minus b ax minus ax b plus b. Okay, right. Now we're going to take derivatives. So take derivatives and set equal to 0. That's what we're going to do next. Wait a minute, what do I mean by take derivatives? This is something that's a little funky. Right. What it means is, remember what does it mean to use this derivatives thing in calculus? It means if you take a small perturbation off of there and take the derivative with respect to it, it gives you to 0. So basically here, we're going to need to sort of soup this up a little bit. Let's replace x with x plus ty. This is a scalar. This y is arbitrary. And we're going to take a derivative, d by dt, and we're going to evaluate t equals 0. That's exactly the same sort of thing you do in calculus when you're trying to optimize, but we need to be a little bit more careful here because there are a lot more variables floating around. This is multivariable calculus after all. Right, okay, so here we go. Let's pick up this formula. And let's say, what do we want? We want 0 is equal to d by dt, t equals 0 of, okay, now I'm going to paste and modify. So let's see, that x, wherever I see an x, I'm going to be fancying it up by calling it what? I'm going to be calling it x plus ty. Right. Okay. So here we go. I guess that copy wasn't so helpful. Okay. X plus ty, ax plus ty. Now up here we're going to have minus b way, that's just going to go away when we're taking derivatives anyway, so we can drop that right off. Okay, you can see things are going to get a little heinous real quick, in fact. But it's not too bad. Let's see here. So, let's see. Remember, we're going to take derivatives with respect to t and set it equal to 0. So anything that's remaining is going to have a t in it. And in fact, it's going to have a t and only one t in it. Alright, let's keep that in mind as we write this out. So, for instance, when you do out this manipulation here, you'll see, let's see here, that an ax, that's going to be going in the trash, plus, let's see, there's going to be a t, t, a, y, a, x, and there's going to be a t, that's going to be a, x, a, y, and there's going to be a t squared, a, y, so that's all from the first term. The second term has got a minus b, ax, that's going in the trash, minus t, b, a, y, and the last term is going to have a minus ax, b, minus t, a, y, b. Okay. So let's get rid of the terms that are going in the trash. They're out of the picture. And oh wait, there's one more. This one too. Okay. So let's see here. And notice here something really nice about this situation here. We're taking derivatives with respect to t. So we really didn't even need that product rule that I wrote up there, although it's awfully handy to think about. So let's see here. There is an a, y, ax. There is an a, x, a, y. And there is a minus b, a, y. And there's a minus a, y, b. Now if you look at this, you say, well, there's a lot of a's, y's floating around. Let's group them. And that's the right thing to do. So let's group everyone who's got an ay in front. And there's an a, x minus b. And there is an a, x minus b, a, y. Now, something's interesting is going on here. See, we wanted these to be both 0. Well, and we've got these y's floating around. Now, y is arbitrary. So really, what we should do is we should rewrite this a little bit. We want to bump that ay. We want the a to be bumped over to the other side. And this is where, remember last time when we talked about Hermitians, we said a Hermitian matrix is one that doesn't change when you do this. Well, in fact, it doesn't change when you bump it over to the other side, but a non-Hermitian matrix, in general, just picks up, it turns into a different kind of linear operator over there. It's called a Hermitian. We usually write it with a star, like this. So I'm going to say y, a star times ax minus b. So this a star thing is the Hermitian of a. Always exists, so you're in good shape to write it. Okay. So what we're trying to solve here is we're really trying to solve, this reduces to a star ax equals a star b. Since y is arbitrary. That non-degeneracy of the inner product is being used here. Okay, well, how do I solve this equation? Well, heck, what we do is we say, well, remember what we're after. We're after x, right? So then x should be, and oh, look at this, something funny has happened. Even if a were not square, this a star a, this guy here is square. This is, Furthermore, what's really nice about this is this guy always has an inverse. That's a fun little exercise. At least if you're dealing with finite dimensional matrices. So then what do? Well, we just write down its inverse. And we're left with this. So in fact, we were able to solve the problem. So what's really neat about this is this thing here, this guy is the least squares pseudo-inverse. It's usually credited to Moore and Penrose. It's found in Wikipedia under the Moore-Penrose pseudo-inverse. But handily also, you can actually access this one pretty nicely in NumPy, SciPy, or in MATLAB type languages pretty easily. In fact, MATLAB, it's wicked easy. It's just backslash. In NumPy or SciPy, it's pinverse, something similar to that. You can look it up. In any event, what this does for us is this gives us a way to solve this equation. What does it mean? What it means is let's now scroll up a little bit in our computation here. Let's look at this line. What it's saying is it's saying that the error, it's saying that the residual, the error which we tried to get rid of before, this residual error, is orthogonal to the range of A. So what it's saying is that, draw a little picture here, there's your vector space V. Here is the range of A. This is what you could have an output. If your B is right here, there's B. What it's saying is that the best choice of X is the one that lands you right there. Closest to B, but not any better. So that's what it does. Now, why did we go through this? We went through this because this least squares game is an excellent way to study approximations, which is what we're doing when we go down the path of Fourier series. So I have one more video after this, which talks just briefly about where we're going with regards to approximation and where we're going with regards to Fourier series convergence. So I will see you then.